按照你是说他谁？是他啊？Testing 1 2. Very good afternoon to everyone. Today the weather is quite good, sunny day. I have marked your midterm exam, but we won't discuss the question yet because there's still 3 more students haven't taken the exam. Maybe the week after next week, we'll have chance to give back to you, and then we will discuss the question together, and then see if there's any revision need to be done. And I got mark statistic with me. Maybe I'll try to review some of the mark during the tutorials, and we'll talk a bit about the average and then so on. The mark with me is just raw score, subjects to scaling and revision later. So it's just a basic marks for now. Just to remind you that you need to pass both your quiz and midterm with 40%, and then final 40%, and then altogether 55% only you can pass the course. Okay. Yeah. Okay. We will talk more about the marks during the tutorial times. And then just to remind you that next week, I think it's next week, we got the quiz again on the counting and relation, mostly last week's stuff. Okay. third quiz. And then 2 more quiz, then will be final, and then teaching the course. Okay, any question for last week? For last week, lectures or tutorial? Any question? Any question? Hopefully still okay. Okay, if you have any question, just bring it up next hour or during the tutorial time. Okay. Okay, just remind you that last week where we stopped, we stopped at equivalence relations. Okay, equivalence relation on the set A. Okay, so when is it equivalent relation? How is it equivalence relation on set A? First of all, it is a binary relation from A to A. Okay, and then the relation is reflexive. Okay, it's reflexive. Three, it is symmetric. 4, it is transitive. Okay, so remember what does it mean by reflective? Reflexive. Okay, for every element in A comma A is in the relation. Okay, how is it symmetric? If AB is in A, then BA is also in A. Okay, symmetric. So if swap is still in the relation. Hey, sorry, in the relation. Okay, not in A. Okay, it's not A. So R is a subset of A cross A. Okay, so that's why I can use this element notation because R is a set. Okay, it's an ordered pair set. And then this one is for all A, B in A. How about transitive? If A, so maybe I write down here. If AB in ABB DC is in R, then AC is in R. Okay, for all A, B, C in A. Okay, so these three you need to memorize or understand it. Okay, and then we talk about the example about the congruence mod. Congru. How to spell? Congru, what does suddenly forgot? Huh? GRUE, NCE? Is that right? Okay. Suddenly forgot how to spell. Congruence, we look at this congruence mod 7. So we think of it as, for example, a okay. So last time we said that equivalence relation partition the Z. So this is a relation on Z. Okay. And then we can partition the Z into 7 pieces. Right? How many pieces? No. 1, 2, 3, 4, 5, 6, 7. Okay. So we can partition the set using the equivalence relation. Okay. Remember? Just recall from last week. Okay. So today we will see how an equivalence can give a partition on a set. Okay. Okay. So any question on the material we touched on just now? Recalling? No? Okay. So let's look at this theorem here. So let R be an equivalence relation on set A. Okay. And then the following are equivalent. Okay. That is for every A and B in A related to B. 2, the equivalent classes of A and equivalent classes of B is the same. 3, the equivalent classes intersect equivalent classes of B is non-empty. Okay, so what does this the following are equivalent? This means 1 can implies 2, 2 can implies 1, and then 2 can implies 3, and 3 can implies 1. Okay, so it's like a circle. Okay, this is the what this theorem the following are equivalence means. Okay, so anyone can implies anyone. Okay. So how to prove this statement? So the strategy we will use is prove 1 implies 2, and then 2 implies 3, and then 3 implies 1. Okay, then we will form a cycle. Okay, so in this way, 1 will implies 2, 2 implies 3, 3 will implies 1. But how about 2 implies 1? So you just go from 2 to 3 and then to 1. So you can get the error back. Okay, and so on. So we will prove all the errors just using a cycle. Is it okay? No question on this part? Okay. So proving this is equivalent to this. Everyone got it? Everyone got it? So here got 6 errors. We just need to prove 3 errors is enough. Okay. Any question or not? No? No? Okay, then so let's prove these 3 errors. Okay, let's prove this 3 errors. So first we prove that implies 2. Okay, so we want to show 1 implies 2. So we want to show the equivalent class of A is equal to equivalent class of B. Okay, so because equivalent classes are set, right? So this equality is actually equal as what? Set. Okay, so this means we need to show A is a subset of B and B is a subset of A. Okay. So recall the set theory. We want to show equality of set. So so this means you take, right? Okay, so this means take an X in the set of A. Okay. Okay, let me write in this way to show. Okay, take an element in A. Okay, and we want to show that F is in B. Right? Okay. So if X is in A, then by definition, by definition of equivalent class, X is related to A, right? Okay, maybe I use this notation. S is related to A. Okay. We know that A also related to B. Okay. Correct. So by the transitivity of R, so our relation is a equivalence relation. So equivalent relation is reflexive, symmetry, and transitive. So by the transitivity of R, X is related to B. Okay, since X is related to A and A is related to B. Okay, since S is related to B, S is, it implies that X is in the equivalent class of B, right? Again, by the definition of equivalent class. Okay, is it okay? So this one, this proof is not long, but you need to like keep reminding you the definition. You need to keep applying the definition. Okay, nothing tricky here, but you need to keep using the definition of equivalent class transitivity. You need to keep using it. Okay. So if you can go through this proof, then you will like familiarize with all the properties. Okay. Any question on this part? No question. Or blur already. Any question? Any question? No? Is it following or not? Following? Hmm? Any response? If no, you can say no. Following or not? Huh? Yes? Okay. Okay, so similarly, okay, exercise you can show that B similarly show that B is okay as okay. And then the next one is to prove second. Should I do the proof on maybe? I think keep continue, you will get a blur again. So maybe just left as exercise. So do you want me to do, or you want to left at exercise? For 2 implies 3 and 3 implies 1. You want me to show it, or you want to try first? Huh? Show? Okay. Show both or show one of them? Huh? Both? Show both? Okay. Okay, then okay, we will do the okay. But this one I left an exercise because it's really similar to the argument here. So you can just run through the argument with a B and A swap. Okay. So next, second, we will show that 2 implies 3. Okay. So 2 implies 3, meaning you need to show that, want to show that A intersect B is not empty. Right. Okay. Since A is the equivalent class of A and B is the same, so this two set is the same. You want to show the intersection, right? then A, they are the same. So you take the intersection, right? So what's the intersection? It's equal to A or B. So why? So the question is why the equivalent class of A is not empty? Why? Why the equivalent class of A is not empty? Hmm? Huh? What's the element inside the equivalent class of A? Hmm? Equivalent class of A is the element, all the elements that are equivalent to A. So what is in there? Huh? What is in there? What is in there? Huh? Because A itself is in the equivalent class, right? Since for every A in A is in A by the reflectivity of A of the relation. Okay, so it's not empty. Any question on this part? Huh? Okay. Any question? No? Is it following? Still following? Okay, okay. I see some nodding head. So let's keep going. So third, we show that 3 implies 1. Okay. So 3 implies 1. So you need to assume that the intersection is not empty and then show that there's relation between A and R. Okay. So if the two set has non-empty intersection, right? And then you want to relate the two elements. Can you do it? What property should you use? Hmm. Okay. Since the intersection of A and B is non-empty, okay, then we can find an element, call it C in the intersection, right? Yeah. Since C is in A, that means C is related to A, okay? And since C is also in B, okay, C is related to B. Right. So if C is related to A, C is related to B, can you show that A related to B? Can you show that A related to B if C related to A and C related to B? Can you show it? Hmm. If C related to A, okay, and C related to B, can you show that A is related to B? Hmm. How? Let me close some name here. This one is group 2. Rainy Chin. Who is Rainy Chin? Right, Rainy Chin. Can you show that A related to B if C related to A and C related to B? That's what? Sensitivity. Okay, how? Ah, okay, I show you the sensitivity. Like this. AB, BC, then implies AC. Okay, and then here. Huh? Same thing. So CA, CB, how to combine become AB? Huh? 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 You don't know? What? You don't know? Yeah, okay, use transitivity, but not in the right order, right? Isn't it? Huh? So how? One more step, one more step, one more step. Huh? Anyone can help or not? I hear something correct. Huh? Symmetry on who? Yeah, okay, you can use symmetry here. Okay, turn this become ARC first. Okay, let me write out the word state. So AR, okay, thank you. ARC symmetric, right? Okay, then together AB, CB, then transitive, you will get ARB. So I just combine by symmetry, symmetricity, how to spell it? Why I forget every English word today? By, I think this is not right. By I think actually correct. Okay, actually correct. By symmetricity and transitivity of R, okay, we have A related to B. Okay, good. So we have proof 1 to 2, 2 to 3, 3 to 1. So we prove the cycle. So we prove all the cycle here. Okay. Okay. So what does this theorem tell us? Okay. So let's come back with this statement again. So it tells us that if we have a relation, okay, if we have a relation, and then we look at the equivalent classes of our element, as long as they are related, they stay in the same equivalent classes. And then if you okay, maybe you can imagine a situation using the Z mod 7. Okay, so for example, you have 0 is related to 7, right? And then you can form the equivalent class of 0 and form the equivalent class of 7, right? And then you will check that their intersection is non-empty. Okay? In fact, they are the same. Okay, then this will prompt us to a definition. Okay, prompt us to a definition. So I keep talking of partition, right? But I never define it. So because I want you to like guess it. So today we will go into the real definition. What's the partition of a set? So a partition of a set is a collection of disjoint and disjoint non-empty subset. Again, subsets. Remember a subset of X that X has their union. Okay, so in other words, again, this one is more useful in a set notation. In other words, you have a subset of X, okay, subset of X, so your index set forms a partition of X. If and only if, okay, this form is very useful. So every subset should be non-empty, okay, and then the intersection is empty, pairwise empty, okay, and the union should be the whole set. Okay, so this is like our Z. Remember the Z last time? Okay, so we have break the Z into 7 pieces. 3, 4, 6, 7. Okay, this one not 7. Okay, maybe use yellow. An example. The color set. So in this case, our I is like in 1, 2, 3, 4, 5, 6, 7. I is the set. So Z is we will write Z as the sum of what? Is the sum of union of I, where I going from 1 to 7. Okay. So I write this right because this is a disjoint union. Okay. So union is like this, right? Union is like this cup, but I write like this because I know that between the set there's no intersection. So I write like this. Okay, disjoint union. So going from 1 to 7, the index set. Any question? Any question or not? No? Okay. Okay. Okay, partition. So disjoint union of non-empty subset. Collection of disjoint non-empty subset. Partition. Okay. So I should say that this one is A1, A2, A3, A4, A5, A6. Okay. If you don't understand this definition here, you should at least understand this example. And then use this example to understand this definition. Okay. Okay. So if you don't understand this definition, you should understand this example. Okay. Okay. So actually, we have the converse of the statement that we make. So what did we say last time? So we say that okay, let be an equivalence relation on X. Then the equivalence classes of R form a partition of X. Okay. So we have equivalent classes, right? And then we take the equivalent classes, and then this equivalent classes will partition the set disjoint union. Okay. Disjoint non-empty subset. And then converse if you given a partition, okay, actually they define the equivalent classes. So we have converse. We have the converse here. So going backward. So equivalent classes form a partition. If let's say I give you a partition, okay, then actually those partition will be the sum equivalent classes of some relation. Okay. So conversely, given a partition, of that x, then you can find equivalence relation that has the that AI as x. Okay. So yeah. Okay. The first statement is obvious from the previous theorem, right? So previous theorem is this. This is the previous theorem. So if they are not related, then the intersection should be empty. That's why you can split the set by equivalent classes. Okay. If you want to see the detail, you can go to the textbook. But one thing maybe not obvious is the converse. Okay. How given a partition, okay, you can produce a relation. Okay. Given a partition, how you produce a equivalent class. Let me think. Yeah. Okay. So, given a partition, how you give an equivalence class? You want to see examples or examples? You want to see examples instead of formal proof? Examples or formal proof? What? Why did you look at me? You want to see examples? Okay, see examples. Okay. Maybe we don't look at the proof. Yeah. Okay. Let's use examples to explain them. Okay. So for examples, let us look at the set B contain 1, 2, 3, 4. Okay. So I give a partition. So the partition is I partition 1, 3, 4, 2, 4, and 3. Okay. The claim is this is a equivalence relation. Okay. This means first it is a relation. So it's a subset of S cross X. Okay. How to make this equivalence relation? Any idea how to make equivalence relation? So from this partition, right, we need to first satisfy the reflexivity. So 1, 1 will be in there. Okay. 2, 2 will be in there. 4, 4 will be in there. And then 3, 3 will be in there. Okay. And it has to satisfy the every equivalent class have to satisfy the symmetry. So you will have 2, 4, and 4, 2. Okay. And then I think you are getting blurred. Are you blurred or not? Anyone still following? Huh? No? I think you are quite blurred. Is it blurred? How to explain to you? Okay. So now given a partition, right? My goal is to create a relation. Okay. So what's the relation? So relation on X is a subset of X cross X. This one, okay? Following. Okay. And then so this set here should be some ordered pairs. Okay. And then this ordered pairs need to satisfy what? The reflexivity, and then symmetry, and then transitivity. Okay, all these you need to satisfy. But inside the same subset, we say that these elements are related to each other. So automatically we will have 2 related to 4 and 4 related to 2. Okay. And then in this set, so 3 related to 3 and then 1 related to 1. And then I claim that the relation is equal to this set here. Okay. Which satisfies that. Oh, I forgot every English word today. How to satisfy? Okay, satisfies. Okay, okay, English better. Which satisfies. Is it correct or not? How? Oh, SA, right. That's why I feel so many S, so many T inside here. Okay, so which satisfies the definition of relation on X and the reflexivity, symmetry, reflexive, and transitive property. Okay, so you need to check all these, and then yeah. So actually, one can guess what kind of a not real, I mean, one possible relation of this is. So this relation is actually A and B is in the relation if and only if A divided B. Okay, so this is the relation actually I'm intended to put on X. Okay, so this is the form of this relation here. Okay, because 1 only divide 1. Anyways, I write on. I shouldn't put 1 because 1 is a one. Oh, because this is not a equivalent relation. Okay, never mind. This is not true. Okay, that's all. Okay. Yeah, so this is the relation. Because some student ask me, isn't it relation? You need to tell me how to relate the two things. Right. But remember, I define the relation as a subset. I don't need to tell you between these two things, how do I go from I don't need to tell you how to go from 1 to 1 actually. I just need to tell you a subset. So relation isn't that I need to tell you how to go between these two elements. No. As long as I give you a subset of this Cartesian product, then it is a relation. Okay. You get it? This is a key point here. Okay. relation is defined as a subset. It's not a way to get from one element to the other element. This is not how we define a relation. It's a subset of Cartesian. Okay. Okay. This is a key important idea here. Okay. Any question up to here? If not, we will go into the next part. Any question? Any question here? No? Should we stop first or should we continue? Maybe take a break. Okay, maybe we take a break and then we come back. 4:53 and then we come back. And then we will talk about statistics to cheer you up a bit. Okay.会乱吗？会乱吗？怎么问？我们开始哪里？怎么说呢？不知道那个theorem 在说什么，是不知道那个定理在说什么。所以如果对，因为不理解的话，不知道要证明，对，应该要解释所谓的那个。每次教你们就感觉有教太快的感觉，因为我不知道你们什么不懂，然后我看到你们就很 blur 了，过后第二天我会在那个部分先再讲多一些东西，他们就没有这么晕。所以你们能够尽量就把暂停这样，然后就会再讲多一些东西。如果看不懂那个 statement 的话，应该要再叫我再解释东西，然后我在证明之前你就把我听进去，再问清楚那个题目要干嘛，我再解释东西。因为有时候可能我看了很明显，所以我就讲太快。啊，
你讲的不太懂。
哪里？
看我这个有点一样的。错的。就是这个的意思是不相交集。
对。
那相交集都是
不相交的并集。
并集。好，那
语连。
那然后这个是什么东西啊？
这个是上个星期说的。
上个星期这个
还记得吗？就是我们把那个 Z 分成7，就是如果是 mod 7的话，我们把它分成7个区块。
这是干嘛的呀？
就是比如说
所有的都在这7个里。
对。因
为 mod 7它一共有7个
equivalent class。对，没有错。
然后对，然后我们今天证明了，如果他们两个是没有关系的，他们的那个 equivalent 它是 intersection 是 MD，
那不是 MT，
因为这个是有关系嘛。但是如果你把它 contra positive 的话，对吗？没有的话就没有 not 对啊，所以我们才有这个 partition 的呀。嗯
这什么意思？
哪一个？
这个
啊，这个是说如果这 form a partition 的意思就是这个嘛 ，collection of disjoint non-empty，所以这里面的东西都是这个 x 本身的 subset， 然后这是它本身的 subset， 然后 form a partition 就是说你拿它的 ，OK， 这句话的意思其实就是这一句 ，OK， 然后这些 A1 是 x 的 subset， 然后每一个本身都是 empty set， 所以它们是 non-empty， 对吗？都是 empty set。AI
跟 I 什么关系
？AI 跟 I， 哦 ，I 是来怎么说呢 ？label 它，就是比如说，比如这个是一个，这是第二个、第三个、第四个、第五个、第六个、第七个的标记嘛，对，标记，对，然后它们之间的交集是零哦，是 empty set 哦。因为我们上面 proof 过了，如果他们没有关系，他们的交集是零的。
这个意思就是 A1 并 A2。
对。
这里面这个 I 就是1到7。
对，我就写这边 I 是1到7，对啊。所以我是说，你们如果不明白这个，你就看回这个，看完这个然后理解这个。
partition 什么意思
？partition， 你说中文还是概念还是？
概念
哈，概念就是你看你有 Z 嘛，有很多东西，但是你可以把它，比如说你们这么多人分开，你们就分成4组人哦，这 partition 成4咯。你看没有交集吗？你不可能你同时做两边的嘛，对，所以对呀，所以如果我说你们一整排有关系的话，这样我们就把你们分成4个equivalent class 成。
可能吧。你看哪里不懂啊？这个懂吗？
这是什么东西？
这个不懂。
这个是什么东西？
这个多写都不太懂。
啥？
这
也是对。这个一看就不懂。
哪个？
现在再说一下。
OK， 我再说一下。这个第一句就是说 equivalent classes of R， 所以你 R 有一个 equivalent relation 嘛，对不对？equivalent relation 过后，你就可以 form equivalent classes 哦。你就看谁和谁是有关系的，对。然后你就有很多个 classes，像这个情况，你就想它有7个 equivalent classes 哦。然后7个 equivalent classes 我 form a partition of X， 所以它把这个 Z 拆分哦。对，这是这一句。下一句是说，他说他的 converse 是对的，就是说，如果你 start with 一个 partition， 你就可以有一个 equivalent relation。
没听懂。
如果什么就有一个。
如果你不知道这个 mod 7的东西，但是我告诉你，那个 Z 可以分成7个部分，对，就代表有一个 equivalence relation 在这上面。
当然会有P 推的关系。
还会有什么？
这点是什么意思？这个
并集 A1 并 A2 并 A3
对
并到 AI。
对。这个是反的，就是我们从一个 equivalent relation 我可以拿到一个 partition， 现在是可以从 partition 拿到一个 equivalent relation。
写的是那个，就前面讲那个 transistor 啊什么那3个关系。
不是 trivial classes 是那个 set，就是 element 之间有关系的，我就把它组成一个 set。
那这什么意思啊？Equivalence class
就是这7个东西是7个 equivalent class。
的那个什么代表的东西是一样的。
这7个 equivalent classes 可以 partition。可以，你可以讲为什么是一样呢？因为它符合这个 partition 的条件。因为它符合 partition 条件，所以我们也可以这样子。
他这样做的原因是为什么？他是想告诉我什么？
告诉你，我可以把这个 z
就把一个 a 乘 a 变成把它的子集全部找出来。
所以你说谁？你说哪个 partition 还是这个 relation 还是 partition？
partition。
partition 只是把那个 set 拆成
对，拆成它
几个部分，
把它的子集全部找出来。
不是，就把它的
我们学这块的原因是，就是我们想通过这个来干什么？我们
通过这个部分来分别给你一个关系，给你一个 equivalence relation， 你可以把你的 set 全部
对，然后
相当于是个
就是通过就是把
相同的东西把它组合起来，对，
就把相同的东西放一起，
对，
分类，
对，OK， 分类呀，分类。
这个是 partition。
Yes。
那这个 equivalence class 是什么意思
？equivalent class 是
跟 partition 一样的。
不是 equivalent class 是你有一个 equivalence relation， 告诉你谁和谁是一样的，然后这些一样的东西，我们可以把它组成一个 set， 就叫做 equivalent class。对，对吗？
然后你刚刚在底下不是写了一个关系吗？但是你又把它擦了，就是你的 A
个
B
这个。
对，你在这儿写了个东西。
那个是错的，不用紧，那个不要管它，那是错，不要理它，那是错，耶。
那就比如说这个，
对，这个
R 就是 S 乘 S， 那
然后对，然后
R 是 S 乘 S， 然后我把它 partition 的话，它可以通过不同的关系，就是比如可以是自反，或者是
都是自反，
自反就是reflexive
reflexive OK，
然后就可以就把它们只要符合 reflexive 的全部找出来。
对，
然后还有那个
全部 transitive 的也找出来，然后把全部找出来。他就
这句话什么意思？
哪一句话？就是 R，因为我没有写这句，我写这句的话，那我问你 R 是什么？什么
？R 是一种关系。
R 是一个关系，所以我告诉你 R 是一个关系。
那个是 S 的一个关系，是个量词。
对吗？OK， 我再讲一次，在本上。Hello, testing. Okay, I think I did a bad job in explaining the theorem, so that's why maybe you're confused with the statement. So, okay, maybe I do a summary slide here. Okay, so first we start with a equivalence relation. Okay, the set X. We start with an equivalence relation on the set X. Once we have the equivalence relation, then we will know that how two elements in the set is connected, right? It's related. Okay, so we know, for example, like we know how two elements are related. Okay, this okay, right? And then we will put maybe write this. We'll put all the elements that are related into a set for the equivalent class of A. Okay. And then the claim is the equivalent classes of R partition X. Okay. So what is the idea of partition? So for example, all of you, okay, student of discrete mathematics, and then we got 4 rows here. So these 4 rows will partition you guys, right? So if I add all of them together, then you are all the students, and then no single student can sit on 2 rows at the same time, right? So there's no intersection between these 4 rows, no non-empty intersection. Okay, so these 4 rows here will partition the students. Okay, so this is the idea of partition. So you also should keep this example in mind here, because this example is a equivalence class example. Equivalence relation, sorry. So there are 2 words here you need to keep in mind. So equivalence relation and equivalence classes. Okay, one is relation, one is classes. The important thing is not the front, it's the back. Okay, let me. So we got 7 equivalence classes in mod 7. Okay, congruence mod 7 on the integer. So the claim is this 7 classes will partition the Z. So every integer will belong to one and only one of the subset. And this is what the partition means. And then the second claim is, if you start with a partition of X, okay, then you can find an equivalence relation not classes, relation of X. Okay, so second claim is you start with a partition. Okay, you start with a partition and then can define the equivalent classes on the set. Okay, this is the claim. So how to prove it? You can go and check the textbook, or you can study this example here, and then generalize to general set. Okay. Okay. So this is the claim. If you don't know how to prove, it's okay, but you need to at least appreciate the statement here. Okay. Okay. So this is summary of the first hour. Second. Okay, second. So go to the next part. So the next part is called partial ordering. So just now we care about 3 properties, which is reflexive, symmetric, and transitive. So now we change the symmetry part, become anti-symmetric. Okay. So a relation R on a set X is called partial ordering, or partial order, if it is reflexive, okay, anti-symmetric, and transitive. Okay, so usually we will write denoted by X with the relation, okay, which we call it a poset, okay, or a partially ordered set. So it's a set, it's a poset, partially ordered PO poset. Okay. So we will write denote A less than B if AB is enough. Okay. If okay. Okay. So for example, we encounter it is Z with the divisibility, right? So if A divide B, B divides A, then A must be equal to B. So this is anti-symmetric. Example of poset is a poset. Okay. So for example, Z, if you put the greater equal sign, okay. So if A equal greater than equal to B, and B is less than equal, if B is greater than equal to A, then A must be equal to B. So this one is a poset as well. It's a poset. Okay. And then similarly for the subset inclusion. So if A subset B, B subset A is also equal, A is equal to B. So these are all anti-symmetric. So they are all poset. Okay. Remember this notation here? Power set of X. So set of all subset. Okay. You consider all the subset of X. Okay. So next. Okay, following. So partial ordering, we change not equivalence relation anymore. So we change the property to anti-symmetric. Okay, next. So so in Poset, we can compare two elements. So the elements A and B of the Poset are called comparable if either A is less than equal to B or B is less than equal to A. Okay. So they are not so okay. When A and B, okay, I should start like this. When how should I put it? Okay, I should put like this. So if neither A is less than B, no, B is less than A. A and B are no, so incomparable. Okay, so for example, so let's say example. In the first example is the divisibility, right? Okay, so we will say that 2 is less than or equal to B, right? Sorry, B. 4. Since 2 divide 4. Okay. So what is not incomparable? For example, 3 and 4 are incomparable. Because 3 doesn't divide 4 and 4 doesn't divide 3. Okay. So in Poset, there will be elements that are comparable and elements that are not comparable. Right?
So yeah, okay. Okay. And then next. Okay, so after introducing the partial order, we will introduce total order. Okay, so if you have a poset, okay, you start with a poset, and every two elements of X are comparable. Okay, so this means there's nothing which is not not comparable, which is incomparable. Then S is called totally ordered, because you can order everything. So totally ordered or linearly ordered. Okay. And the order you will call it total order. Or a linear order. Okay. And the good thing is a totally ordered set is called a chain. Okay, they form a chain. Okay. So for example, I think the second example form a chain. So this example here. Okay. First of all, this is a poset, right? So the claim is every two elements here are comparable. So they form a chain, right? I think this chain you are familiar with, right? So this chain is something like this. And keep going on. And then this one, this one, this one. Okay? So this is the chain for this poset. Okay? The form a chain. Okay, next. So this is a total order. Okay, next, the last thing is a well order. So in discrete math, right, you want to count, you want to order them. So now we are ordering things. So we have a poset again. If a poset, when is it well ordered? If it is a poset such that the relation is a total order and every non-empty subset of X has a least element. Okay, so you can find the smallest element. Okay, so for example, the natural number is well ordered. Okay, because you can start from 0 and then hit all the way up to infinity. So every subset of n, you can find a least element. But if you consider the whole integer, then it is not well ordered. Okay, because you cannot find the least element if you consider the whole chain. If you consider the whole z, okay, because it keeps continuing to the negative infinity. You cannot find the least element. Okay, so this is the ordered, well ordered. So yeah. Okay, next. So summary. So quick summary on this thing. So we have what? First we have a poset partial ordering. Okay.
which is reflexive, anti-symmetric, then sensitive. Okay, and then next we upgrade to total order. What is total order? So every two elements are comparable. Okay. So remember the divisibility one is not total order, and then the next one is well ordered. Well ordered. Okay. So well ordered means every non-empty subset has a least element. Okay. So of course these are all Poset first. So you are upgrading. Okay. So natural number is a well ordered set. Okay. Okay, next. Next, after we can label order, there's another order, okay, for the lexicographic order, okay, and then this order is actually the order you use in the dictionary. Okay, in the dictionary you use this kind of order. So when you want to find, for example, stars, right, STAR. So you find X first, and then you find T first, and then A, and then you find R in the end. So let's start with two posets. Okay. So what's the lexicographic order? Lexicographic ordering on the poset A1 times A2 is defined by every two couple in the addition product. Okay. A1, A2 is less than B1, B2. If and only if A1 is less than B1 in the first coordinate, or okay, if both A1 equals to B1 and the second one A2 is less than B2. Right. So in the, for example, in the dictionary, right? Dictionary. So what is less than one? So star, okay, let's start with stars. So let me start with, okay, BOW will appear first, then star, right? And then what appear next? Supper. Okay. So you compare the, is less than if the first one already less than, or if the first one is less than, then you will look at the next one. Okay. So this is what the lexicographic order. So actually I talked about only two, right? So you can generalize two, right? More than two. Okay. So you can generalize to n concept. Okay, A1 up to AN. Okay, so this is another kind of order. What's the next thing? Okay, so next thing we will form a Hessel diagram. This is a step before we go to graph theory. Okay, so we'll look at this Hessel diagram here. Maybe I let you see the example first, and then before I describe the step. Otherwise, you don't know what I'm talking about. Okay, let me and here first. Yes. Okay. So we want to construct a Hessel diagram, right? So for example, let's look at, don't look at this first. Okay, so we want to find the Hessel diagram of this, the Poset here. Okay, the Poset here is the set 1, 2, 3, 4, and then the relation is less than or equal to. Okay, so how to get this picture here? So first, you will draw the loop for, you will draw loops, you will draw arrows whenever they are relation. Okay. So 4 is less than or equal to 4. So there's a relation between 4. So you draw an arrow. 3, 2, 1 similarly. Okay. And then 1 is less than 2. Okay, you draw an arrow. And then 2 and less than 1, less than 3, and then 3 is less than 4, and then you draw an arrow. Okay. And then you compare 1 and 3. You compare 1 and 4. Compare 2 and 4. And then you will finish all the arrows. Okay. But Hessel diagram want to simplify this. Simplify the relation here, the arrow relation. So first you will remove the loops. Okay, remove the arrows that go to itself, because you already know that in the Poset you will always have reflexive property, so we don't need that arrow to tell us. Okay, so we'll remove this arrow. Second, we will remove the transitivity arrows. Okay, so all these transitive arrows will be gone, because we know that if in the Poset, if 1 is related to 2, 2 is related to 3, automatically 1 will related to 3. So it's already represented by this straight line here. Okay. And then what else? And then you can remove the arrow after you arrange them. So you start from a bottom element, and then you keep the arrow oriented up. Okay, and then you remove the arrow, keep this orientation, then we will know that the arrow is keep going up. Okay, this is the Hessel diagram. Okay, so let us write down the step. So what's the definition of a Hessel diagram? And then we will do another example. So what's the Hessel diagram about? So a Hessel diagram, the Poset, is constructed as follows. You need to know how to read the Hessel diagram again, or construct even. It's a directed graph. Okay. I will tell you what's graph. Directed is direction. Okay, how is it formed? It's formed by drawing arrows. Okay, from where to where? From a point A to a point B, whenever A and B is in a relation. Okay, so you draw all the arrow with the relation. And then 2, remove all the loops. Okay, remove all the reflectivities. Okay, that one is automatic, so you remove it to simplify the diagram. And then third, then remove all the transitivity edges. Okay, because we know that we can compose the edges. On that connects. Did I use the wrong? Yeah, I used the wrong one. So this one should be A. And then
This one should be B. Okay. Third, okay, arrange each H so that its initial vertex is below its terminal vertex. Okay, because it's a poset, right? So it's a poset, then you can like keep comparing it and then keep growing up, and then you can remove, arrange. Yeah, you can arrange from bottom to top, and then 4 is remove all the arrows. Because if you arrange like that, then we will know that the arrows will all keep going up. So if the arrow is the same, then we just remove the edges. Okay, so try. Let me give you 2 to 3 minutes. Okay, try this question. You can discuss with your friend. Try work out the Hessel diagram of this Hessel diagram of this relation, this poset. Okay. So remember what is, I think in the exam we have this kind of question, right? What is the poset of this set here? So it's equal to the empty set containing A, set containing B, set containing C, and then AB. AC, BC. I think this is almost exactly the same question. Okay, so use this and this relation. Try and draw out a Hessel diagram. I give you 3 minutes. You can discuss with your friend. Later I want you to show me the Hessel diagram, okay? I will simply call person, call student. I want you to show me. What's the Hessel diagram? You want me to leave the definition or the example up here? See example or definition? Example? Example, okay. Try understand from the example and then work out the Hessel diagram. So the question is what is the Hessel diagram for the power set of C, and then the relation is the set inclusion. Okay. Give you 3 minutes.
So you draw arrows for all the relation, and then you remove the reflexivity relation, okay, because it's in automatic in the Poset relation, and then you remove the transitivity relation. Okay. Who is the first one that finished? Can tell me. Who is the first one that finished? You done your thing? You done? Can you show us? See? Let me see. Okay, nice. Hey, hi. Can you like explain to us how to do it? Really? Okay, you want to try explain your solution? 跟解释一下。OK 呢？要 draw yourself.
Okay.
Mm.
你刚才那个呢？
哪个
刚才画的那个啊，对这个。
？OK. 就解释你怎么画的。
首先是
讲一下，讲一下。
first is the
你要画吗？
对，就是那个红红的那个。
OK， laser.
Is the relationship in this is this is
Set
the
inclusion.
set inclusion.
Yep.
Yeah, it's the important yeah,
Part.
it's the most important part.
OK.
And we need to according to this relation between this
Power set.
Yeah, power set, and we need to define all this
Subset.
subsets
OK.
to this power set.
OK.
Now we all know all these are the subsets of this power set, and among all these power sets, these subsets, they have this relationship between themselves as well.
OK.
So we need to first I start off this relationship, and all this can be this
Contain.
Yes.
A subset.
Yes.
Okay.
All this can be its subsets. So first I write. I draw a little dot of it as.
Okay.
Then we consider it as the largest. We consider it as the largest set. And the second largest set it contains 2 elements. So we put it in the next level. Because there's 3 of them, so I draw 3 dots. And we could, and they are in relation of sets, the set inclusion. So I could just line it up. And next is the third level, which is the set includes only 1 element. So we put in the third level. And AB contains A, and then AC contains A. AB contains B, and BC contains B. So then that very least is the empty set.
Okay. Done.
Yes, done.
Okay, thank you.
Yeah, thank you. Okay, so interesting that she used a term called level. Okay, so why suddenly a level concept coming in? Because you will see that the zero set element contained in every set, right? Contained in every set. I mean, it's a subset of all the set here, and then the one element set contained in two element set, and then two element set in turn contained in three element set. Okay, and then yeah, so this is the most simplified diagram here. So you remove all the loops, right? So these loops we all remove because everything is a subset of itself. This is what we proved. The empty set and the set itself is that okay? So we'll remove, and then we also remove the transitive. We know that A is also contained in the set ABC. So this is a subset of the larger set. So this line we also remove. Okay, so this is the most simplified diagram that we can draw. Poset relation, which is the tensor diagram. Okay. Very good. Good. Okay, next. Good. Okay, so next. So you can see that this diagram here, there's some guy at the bottom, some guy at the top. Okay. So there's some features coming out from the diagram. So definition. So an element A in the poset is called maximal if there's no other element such that it is greater than B. Okay. Similarly, an element A is minimal if there's no other element that is less than B. And then the next one is an element A in the poset is called the greatest element. Okay. Element if B is less than A for all B in X. And similarly, an element A is called the least element if A is less than equal to B for all B. Okay, so this should be intuitive. Okay, so maximal is there's nothing bigger than you already. Okay, so the greatest is everything then the greatest element is less than you because you are the highest tallest one. Okay, so let's look at some example. Let me bring out the example for you. Bring out this example. Okay, so from here, let me just erase this first. So we have four poset here. Okay, So if I remove this as well, so Poset here. So what are the so the question is what are the maximal, okay, what are the maximal elements? Maximal elements, okay. So there's nothing that is greater than the elements. So all the top guys are the maximal element. Okay, there's nothing that's greater than that. Okay, these are the maximum. So similarly, what are the minimum? These are the guys that has no one that is less than them. Okay, so you will think, why I still need a greatest element notion here, right? Why should I need greatest? I already have maximal. I already have the top guy. So why I need greatest again? Okay, so let's see is this example here. These examples. So part A. A is the least element in this case. Okay, because no one else is smaller than A. Everyone else is greater than A. Okay, it's called the least. Everyone else is greater than A. Okay, and then there's no greatest element here. Okay, there's no greatest element here because if you are greatest, so that means everything else have to be less than you. Okay, but if you look at B, let's say B is the greatest. Everything here is less than it, but C, there's no comparison between B and C. So we cannot compare B and C. So that means I don't know B is the greatest or not because I cannot compare B and C. Because you need to work. This definition have to work for all other elements in the set. Okay. So in this case here, there's no greatest one. So these three are equally top. Yeah, equally top. Okay. Equally great. For example, how about B? Does B has least or greatest element? No, right? Because you cannot compare A and B. You cannot compare D and E. Okay. So here you have no least. Element. Okay. How about C? Does C have a greatest element? Yes or no? Yes. Okay. So what is the greatest element? Huh? Who say yes? Anyone say yes as well? Huh? D. Okay. D. 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 Yes. Good. So D is the greatest element. Are there any least element? No, because we cannot compare A and B. No lowest. No least element. How about D? D. The graph D. Does it has a greatest element? Yes. So what's the greatest element? D. D is the greatest element. How about least element? A. Yes. A is the least element. Okay. So least and greatest will pick up one, and then maxima can look at more than one. Okay, I think we can finish this chapter after this slide here. And then, yeah, okay. So next, so we will introduce more ordering. So we got maximal order and then least order. Okay, so now let us look at a subset of Poset. Okay, we don't want to look at the whole Poset. We look at a subset of it. Okay. In the subset, we also want to find bounds. We want to find bounds.
So we can look at the subset and then see which one is the largest one. So an upper bound of the subset is an element of X such that A is less than equal to U. Okay. Similarly, this is a bit of extension of the maximal and minimal element. So upper bound is greater than every element in A. Lower bound is less than every element in A. Okay. This is upper bound and lower bound. Then we also can find the smallest one and the greatest one. So the least upper bound. So among the upper bound, among the big one, I can find the least. Like a cat on the subset. The least upper bound of set is the element A, such that if you are upper bound, okay, and second, you are less than all the upper bound, okay. First is the upper bound, second, you are less than all the upper bound. So you are the least upper bound, okay, smallest upper bound. Then the next one is the greatest lower bound. So you can find the greatest among the lower bound. So what's the greatest lower bound? So the greatest lower bound of A, if first of all it has to be a lower bound first, okay, and then it is greater than all the lower bound. Okay. So this is the greatest lower bound. Okay, in a second we will see one example, a few examples. Okay, let us bring out the Poset. Let's bring out the Poset. It's the Poset. Yeah. Or maybe you just copy this set first. Okay. So we start with a subset, right? Okay, we start with a subset. So let us look at the subset. Okay, here's the. So look at the subset ABC. Okay. So what are the upper bounds? What are the upper bounds? ABC. So look at A, B, C. So what are the things that is greater than all of this? Okay. So you can trace it. One of them is E. Okay. How about D? D, no, because you cannot connect C to D. You can connect B to A, D, A to D, but you cannot compare C to D. Okay, so D is not. So E is the upper bound. Similarly, F is the upper bound. Okay, and then J is the upper bound, and then H is the upper bound. Okay, so these two are not. So the upper bound of ABC is E, F, J, and H. How about lower bound? So everything that is less than or equal to ABC. So A is the lowest one. So it is also less than equal to itself because it's reflexive. So the lower bound is A. Okay. How about LUB? So lowest upper bound is what? Is actually E. Right. Lowest upper bound. Because among E, F, J, and H, this one is the smallest one. Okay, so this one is E. And then greatest
lower bound because only one to compare, so automatically A. Okay. So maybe look at which one non-trivial one. Okay. Maybe look at one more non-trivial one. So let's look at BDG. Okay, BDG. BDG. Okay. What's the upper bound of BDG? Can you guess or calculate? Wait, let me write down. So H is one of them. Anything else? H. Anything else? Huh? Anything else? Huh? Anything else? G. G, right? Because G also greater than answer. Any more? Any more? This one cannot compare, so cannot. And then this one cannot compare with G, so cannot. Huh? So G and H. Okay. Yeah, so G and H. And which one is the least upper bound? G. Right. So G is less than H. So it's G. How about lower bound? B. And then anything else? A. Okay. That's all. Okay. And then what is the greatest lower bound? Greatest lower bound is A or B? Greatest lower bound. A or B? B. Okay, because B is greater than A. Okay. Okay. Okay, try exercise. So exercise, try work out, try work it out for the set JH, and I will provide the solution later. Okay, JH and CDF. Okay, last slide. Last slide. I'm not sure this one is useful for you or not, but I'm interested in this. So what we call it a lattice. So let me bring this up. Copy. 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 It's the copy. Copy. Let me just bring this up and then I'll explain. Last slide for today. So today. Okay, so we built until here, so we will form something called lattice. Okay, so we have a poset, partially ordered set, and then if every pairs of the element have both a least upper bound and greatest lower bound, then we will call it a lattice. Okay, so usually in your mind, I don't know, at least in my mind, like lattice is something like this. Okay. So this lattice will fit into this definition here. And lattice is like keep going. Okay. Yeah. So keep going on. So this lattice will form will fit into this definition here. So it's a poset, and then every element, every pair, you can find a least upper bound and the greatest lower bound. So you can find a least upper bound and the lowest lower bound. We already know how to find, right? Just now we have example. So in the tree diagram here, okay, only B is not a lattice. Okay, B is not a lattice. So actually, this kind of graph, this kind of poset is also a lattice. This kind of poset is also a lattice, but this one is not. Or something like this. Why? Because you can found a pair, okay, which is BC, that it doesn't has a least upper bound. So why is it no? So for these two, you got the upper bound here. This is also upper bound for these two. And this one is also an upper bound for this one. So which one is the least one? Okay. So the candidate should be these two, right? Because if you consider these three, these two are lower. But there's no way to compare these two. So there's no least upper bound. So out of these three, B is not a lattice. And for this, you can pick any 2 points and then try to find the least and greatest low. Yeah. So relation will stop with lattice and Hessel diagram. And then the next topic is graph and tree. So graph and tree is the topic that we will spend most of the time, about 3 weeks. So this topic is a generalization of this Hessel diagram. Okay. Okay, any questions? Any questions? Question? Okay, so this diagram, I think, is very useful if you want to build some network or some relation graph, or yeah. Okay. We'll talk more about in the graph and trees section. Okay, if no question, let's come back at 0604, and then we'll talk about some midterm mark statistic, and then do some tutorial questions.
我想问一下，为什么 A、B、C 的上界是 E、F、G、H？
所以你看 A、B、C 嘛，对不对？那你要看大过他们的东西，就是 E 有连接哦，连接去这3个。OK。F 透过 E 就连接去这3个哦，相等就是 J 啊，H 都有哦。但是你要看为什么 D 不是他们的 upper bound，因为 D 虽然大过这2个，但是它跟这个没有关系。
但是 D 不也大于 C 吗？但这幅图里还没有显示出来。
不是，这图没有显示出来，就代表它没有大于。对对对，
这是个关系图对吧？
啊对，就是他们之间没有联系。也，之间没有联系。incomparable。
这个就是换了道题，就是在偏序集region 整除中，然后等3、9、12的最大下，我就问，就是这个偏序集它有上界和下界吗？就一个3、9、12，它是有下界，但没有上界，对吧？
对，没有，它有上界，但是它有 upper bound，但是那个 upper bound 可以无限，就是它
为什么？
为什么？
它的上界是什么？为什么有无限的上界？它既然可以被整除，那么只有1和3。
因为
3、9、12被一个整数整除，那么只有1和3。
哦，没有，它不是被1整除，这个的意思是说，这意思是说，如果你可以 A 可以 divide B，A 和 B 就在那个 relation 里面，所以这个图是长这样的。这图是这样的，所以比如说它是从 Z 加开始，Z 加是从1开始，所以1可以 divide
3、9、12啊，3、9、12
啊，对。但是假设我要把整个图，比如说我包括1、2、3、4、5、6、7、8、9嘛，所以假设我有1，然后9、2。 然后我就有3，然后4就在这里，
为什么不是
就在这里
3？
这是3啊，
哦
因为2不能除3啊，所以2跟3没有关系。
哦，
然后6在那里，6在这里，7在那里，7要除新的，所以第2层是全部的 prime number，
就 prime number。
对，然后你还有10哈，这样画一个10进来，10在这里
8在这儿
，8在这，对
，9的话是
，9的话它可能是在这一层。
哦，对，
OK，所以它可以是这样，然后这样，然后还有怎样？
没了。
还有这样
啊，这本来就有。
，OK，可以吗？所以你现在要看的是
3、9、
39，
12，
哦，还有一个12要
那就39吧，那就39
啊，
那就3和9。
3和9，如果3和9的话，给3和9看，3和9 ，OK， 3和9你要找它的 upper bound 的话，你应该要去找所有可以被9整除的东西嘛，对不对？
被9整除是9被1个整数整除
9被1个整数，
，9可以被3整除。
没有，比如说18是它的 upper bound，
哦，
比如说应该还要更高27啊，然后等等，全部
所以
以上，
它没有最小上限，
它有没有最小的哈？
它没有最小，它没有最大的。
没有最，应该不是最小，因为这2个没关系，所以它没有最小。哎，喂，它是本身呢？最小是它本身呢？
对呀，
啊，最小是它
应该
本身
是
啊，
9啊，
是9本身，因为9也是它是它自己的 upper bound。
但是在这定义的是3、9、12被1个整数整除。
9也可以被9整除。
下去，对呀，所以他是说这3个同时被一个东西除，就是同时有一个除它们的话，就是它的，比如说1、3，然后 the greatest 就是它，
对，这个3是它的
什么 greatest lower bound，
是最大的下阶，
对，
最大下阶。
对，
那它为啥是下阶？
它
为什么是下阶？
啊，下阶是比它小啊
下阶的意思
，lower bound 是
在它们几个元素里边比它们几个元素小，
对，
就是下阶。
对，
如果比它们元素大的话就是上阶。
对，然后我们是对最小的最大那个游戏机跟最大的，因为最大的去到后面就没翻译。
它求那个上下界的时候呢，是首先看一下它，比如说这个，这个是刚才说的，比如说这3个，然后呢，所以说跟这个是处于在同级的时候，它是不可以被考虑的。这2个也是同级不可以，这个是因为没有直接关系，所以不参与这个上界，就不涵盖在上界里。
没有关系，对，没有关系，对。
所以它选上界成。
因为这个跟这个没关系，这个跟这2个有关系，但是要跟每一个都有关系，你才可以。
就是要么是这种，
要每一个都要。
就是要么就是这种线性的，要么就是类似于传递性的，要不然就是那种发射这个辐射性那种，就是每个都要跟它有连接。我想问你为什么不是
这是一个 lattice， 因为 lattice 的定义是说，lattice 的定义在这边。对 ，lattice 的定义是说每个 pair 你都可以找到刚才他们讨论那个 least upper bound 和 greatest lower bound。对，
可以找到。
那你 B 和 C 找一个给我。
是 A 吗？
对，这个是它的 greatest lower bound，但是找不到它的。
B 和 A 是 less upper bound。
但是那个least upper bound 只可以是一个，不可以是2个。
只可以是必须是只有
因为他要符合一个条件是所有其他的 upper bound 都要大于它，但是这个你不能够讨论它到底大于。
所以它是
只可以一个呗，因为是 least， 唯一一个的 list。
老师，我有个问题
Yeah.
为什么这个3跟4是 incomparable？
因为这一个的那个
就这个是一还是除？
除，
这个是除啊。
对，除。
那
那里有除，
那为什么呢？就是它不是这里说是它要 a 小于等于 b， 或者是 a 大于等于 b。
这个大于小于啊，是一种 relation 来的，不是真的小于或者大于。
就是这个它是满足于这个是一个 relation 的。
对，因为我们对，因为你没拍到这个上面，因为在 Poset 的时候，我们是可以比较东西，所以我们把 partial order、partial relation 写成这个符号。因为他们是可以比较的，所以我们写这个符号。
那就是所有的 relation 都是用
partial relation。partial order。partial ordering 呢，我们都可以写成这个符号。因为我们可以比较。
还有一个就是为什么这个 J 不可以是？
不可以是什么？
这个 upper bound 为什么不可以是 J？
OK， 你看这个 BDG 啊 ，BDG，OK， 你要找同时大过他们3个东西。
对。
所以 OK， 所以你问这个为什么不能嘛？你看这个可以大过它。当然也可以大过它，但是问题是它能不能大过它？
但是它不是可以这样。
你看你上来可以，下去没有这个东西我们只知道这个大过这个，这个大过这个，没有说这个 OK， 这个小过这个。但是你看，如果你知道 G 大过等于 H 小于等于 F， 然后 F
就不是大于等于。
对，是 H 是大于等于。那你怎样知道 J 跟 G 的关系呢？你明白吗？要不要给一个实际例子？比如说2大过7， 7大过等于3 ，OK， 然后4大过等于 OK， 这个可能那里干嘛？没签，我还没给。对，会给，我会给。所以你看，我给你看什么呢？这个大一点的3，OK， 你看3大于7 7大于等于1你看2也可以大于1， 4也可以大于1，但是2小于3， 4又大于3所以没有关系。
就是它不能往下的，它就只
是一直往上所以我们才把那个箭头丢掉，因为我们知道我们是可以往上的。OK。Okay, hello, testing. Okay, I'll pass down the badminton here. And then on the exam, I just finished marking on the Sunday for the 200 script. This is the for okay. 54.37. Let me see the other bit. Okay, so the average mark is about 54. Okay, so average is 54. And then in this class we got two which is more than 80, around 82, 83. Yeah.
I think for me, this 82, 83, as long as you can get 80 above, you are about 90, 90%. Okay. So one is Gao Zhenyang. Okay, Gao Zhenyang. Okay. And then the other one is Gu Menghang. Where's Gu Menghang? Gu Menghang. Okay, yeah. Okay, these two. And then above 70, around 70 is about 80 and above. Yeah. So we have Chen Wang Fu Wei. Chen Wang Fu Wei. Who is Chen Wang Fu Wei? Not here. For you. Okay. So your name got 3 characters. I mean your first name. First name. Your last name is Chen, is it? Wang Fu Wei is the first name. Okay. And then Gao Zihan. Who is Gao Zihan? Above 70. Okay. Above 70. Jiang Fangling. Okay. Very close to 80. Maybe you can check your quiz paper, exam paper, see if you can add more. Li Mingjia. Who is Li Mingjia? Li Mingjia. Okay. Very good. Peng Jiarui. Okay, good. Above 70. Ran Qiuzi. Okay, Ran Qiuzi. Good. Qu Jiaqi. Okay, good. Yu Xingyan. Okay, good. And we have Danzhou here. Okay, I know Danzhou. And then next is Rainy Chin. Okay, Rainy Chin. Yeah, Rainy Chin. Peng Xingyun. Okay. You're also very close to 80 already. So these are roll score. So they are subjects to, I'll give back to you after the replacement exam, and then you will check, we will discuss, and then if there's some additional mark we can add, and then also I will scale the exam because one class the highest is 85. Your class is 83, so I'll scale the mark. Yeah, I'll scale the mark. So after I decide how to scale, I will let you know. So in this class, I think no one in the danger of double pass, I think. After I scale, it won't be a fail in the midterm. I don't think your class got this kind of student. Anyway, but I will double check. I will let you know. Because if you fail the midterm and quizzes, then you will fail the course. I'll try to make sure you guys don't fail in the first pass. But second pass have to depend on you. I can't do anything, and then if you pass the 2, and then you still have to pass the last pass, so add up all together. Okay, so I will try make sure you don't fail in the first pass, and then second pass is your effort. So in the exam, right, to get 4.0, you have to work really hard. Okay, I won't make you fail, but I will like keep the distinction standard. Okay, I can't make the exam too easy, and then you get good marks, right? Because otherwise you go up, you are not competitive. Even if you get even if you get offer, but your quality is not there, then it will be hard for you as well. So yeah. So try to keep the quality. So if you can get 80 above for my exam, I think it's quite good already. It's about equivalent to 90% and above. Okay. Yeah. We will discuss the question later. So if you want to see your raw mark, you can come in between the tutorial and then see one by one, don't come in cluster. too many. Otherwise, if no question, you can start do the tutorial. So this week tutorial, we got a lot of equivalence relation. Okay, so you will acquainted yourself with equivalence relation, how to show equivalence relation. And there's a lot of equivalence relation. Also try to do it myself. Do spend a lot of time. Okay, so remind you again, quizzes on equivalence relation and counting. Yeah. Yeah. Yeah, in the meantime, if you want to see your own score, you can come if you want. Yeah.我看出来，你是什么学校？什么学校
DMT 203，
103、
203，
203。分位置，这只是raw score 一条。OK， 只看一下你有没有 fail 吧，先。
帮我看216。
216哈。
DMT。
刘你咩？
不是帮我隔壁
那个。刘千富。
我的是。
你呢？
我是几号？
你几号
668。
668。58。
OK。
多少？141。141，还是你是不同的那个
？DMT 的。
你叫什么名？141，你从1开始哦。哦 ，OK。
错了。你的呢？9。
可以自己加55分啊？
自己加？
没有，你可以想象你加15分过后，
加多少？15分。
大概会这样加，但是我还没确定。
你是998的？988没988，脸色很差怎么办
？988，哦，往前。朱子琪。OK。Yeah. What's your name? 990。62。哎呀。OK， 会调啊就。Are you ready 呢？下面呢？其实没有。可以想一下，差不多加15分这样，大概。再想一下啊。这样。你有什么名？
没有，太低了。
啊？你说我没有。啊什么？
还准备了好久。
你说？31。喂？我别烦了。第2组。你们是第3组吗？你们第1组、第2组，好像是第2组。我看一下OK， 250哈，231。31是王烨。
记，
对啊，
不记啊。
一条一条。
我想看到那个，
你看到什么分？哎，不是什么名？看到了？
我回去了。你往上一点。
晚上什么分？什么名？
张
张不是在下面吗？张在下面吧？张什么？海月。
还没有，他们
若
在看。
禅。问题。海月。会调啊，这个分还没有确定的，这是基本分吧 ？Raw score 是吧？
对，我就是随便看一个。
随便看看。Q 啊，
按学号。
缺哈，缺加一，大概会加个15分这样。乘什么？
不可以。
乘元熙，你同学？
看
65。
66。
嗯，
哎，是哪个？
嗯，
是哪个？
嗯。OK，
就不少啊。
会让你们查那个是吗？
对象
再往下翻。
好像是。什么？
彭旭明。
彭星莹，彭星莹，你是那个曼来的对不对
对，
？OK，还有一个还没到。
我和孟涵都是。
孟涵，彭星莹，哎，又找错了。彭星莹，
应该是最下的。
79。
上司聪明
啊，
上司聪明。
S 标
84。
我没有看，
我也没看
是吗？
我
这只是 raw score 会调。
低，
谁？
我看很多。
语文前面
6
对
60
L 什么？李嘉玲，李嫣然，
赵一航在。
在哈。一航都会调啊，这是 raw score 吧？基本分吧。
调是减还是增加先？
增加啊，还会再，因为那个平均分有点低，所以会调一下。你是什么名？
没有看见，我看见，我跟你讲，
17。
你叫什么名？
只要我上面
不要啦，
你跟我讲啊。
没有，
我不会看，你跟我讲啊。
我是
我只要认一下人脸。
我是刘伟斌，
刘伟明啊，
刘伟斌，
刘伟斌 ，OK。所以要看你什么名？672。67。好。67。
猜到我说人40多。
253。253啊。253，这个是那个女同学呢。
后面的不要过来。
253。你告诉他只是 raw score 吧，会调。应该不会 fail 啊这个分，因为我会上调蛮多。哪一个？谁？又是 X。X 什么
？S
什么 X？这个啊，详细。S 这个孙哈，还是少苏哈，孙爱玲这个会调啊，这个是 raw score 吧？对，还有谁？
温东林，
啊，哪一个是温东林？这个 OK。有一个。你们很多好像是没有解释这个啊，全部 true false 是吗？等下你们解释没有解释？OK，会给你们看一下那个考卷，是下个星期的。你看，还有谁
游戏。
？Li 李什么？
灵
异呀？
我看到了。
看到了？灵异在哪里？好，灵异 OK。 喂，sorry，
我帮我
所以
同学看
他的小
你谁？
玉心言，
你可以看啊，
我同学的玉心言，
于心言，
哇，
你同学在哪里？那个坐你旁边呢？
嗯，
于心言啊，加45分应该是80多。看谁？能看一下汤书凯。汤书凯，这个不错，不错。还有谁？
陈王富伟，
王富伟不是坐那边吗？
他太远了。
王富伟是什么字啊？为什么有4个？哦，王是他妈姓是吗？啊，OK，
看一下216，
你不看你自己啊？
216就216，
你不看呢？哦，看到了，
看到了
这个，OK，你呢
216，OK，
你是不是没有解释这个？好像
嗯，
你没有写解释啊？你是 true false 是吧？对不对？
我写了呀，
你有写吗？
我写了，
好像可能不是你，很多人没有写。看，我派回来再看一下有问题吗？你再调，
我写的比较紧，
没有写的对就行。
我写了呀，
如果有写的对就行，
流星，
是吧？
流星，
流星，你要告诉这个只是 raw score 哦，流星啊，前面不重要，因为会调。还没来啊？
没有意义。
呀，没有会呀。哦，你看，OK，还有吗？还有谁？252，哦，252，你是252？你是252
Yeah.
？Indonesian 啊？
Yeah.
Oh, Indonesian. Okay. Oh, you speak Chinese like Chinese one.
Very low. Okay.
Okay 啊 ，OK
Thank you.
OK，
670，
670，这个应该不会 fail 啊，我会删条
我可。以看一下那个，
应该不会
帮我看一下6
6什么
666啊
666
663
663，好像没有663 668吧
668再给我看多一下
，668还可以
你可以看那个33的盘了。
33的盘，
哦，
你在哪里啊？663没有看到663，33的盘。
那我最后一题做完，
对啊，你最后一题怎么没有拿分？那送分了，
我
来不及了。
那个做法做错了，可是我想不起我做错什么，然后我就
OK，OK，OK
用计算机找出来。
好，OK，
第3题超多的0分的，
呀，第3是什么？
第3是证明题，
哦，呀，对，induction，
然后多一元。
好像有人满分呢。
那个我看到要 proof 我就跳这行。OK 了，我来理解。
呀
989。
，989，989不会 fail 了，38，拿到10分的话，可能就我救不了你们了。10分呢，有人拿10，没有，我会 scale，怎样 scale 我之后再调看，再跟你讲，不会 fail 这个分，会的，10分就会 fail，我不知道怎样救那10分了，那种10分不懂讲不会做。你呢？
我这个怎样看？
你是谁？
这个你的 number 是几号座位是吗？哦
，ID 吧，你什么名字？
我看到了。
你谁？啊，Seng 看，Seng 一下，不会 fail，我会调，Hello. Yeah. So these are just raw score. Just keep in mind these are just raw score, and then we will revise, and then I will scale it as well. Okay. I think in your class
no one will fail in the first pass because I think only you get 10, you will fail. I cannot help you with 10. I cannot scale from 10 to 40. Right? If 20 something, okay, yeah, I can scale. Yeah. 10, I cannot. What happened in the 10 sheet, the 10 exam sheet is he don't even know how to count the GCD, and then all the simple counting also don't know how to count, then you cannot. So that means you are not learning it from the class. Yeah. You all the simple counting you also cannot count. Okay. Yeah. So actually I set a base question that you can attend so that you won't fail, and then middle question, medium question, so to get 50, 60, 70. Actually, all your cohort will accumulate at around 40, 50, 60, 70. Yeah, 50, 60, accumulate them. And then for who can answer the proof question, they will go above 80. Those can answer the proof question, and then, for example, question 1 is the concept question, they can handle it well. Concept question, proof question, handle well, above 80. Yeah. So this is how the question are set. 它只要保证里面是平在有些都有问题。比如说这里只有二反式，比如说我这里面如果有个3D 的话，这样它就没有，这样它就不算是那个反式。啊，OK。里面区的话，比如说多少在一个房间的那个。 Yeah, there's some correlation between your quiz mark and exam mark. I noticed that if you done poor in the quiz 2, you basically your midterm is not that good. So make sure for the quiz, you need to try to score good marks, because the quiz is like a small test whether you understand the parts or not. And then the midterm exam or the final will be tested on every part. So even if you don't do good during the quiz, you should like understand it afterward, so that for the final then you will perform. So so you still need to work on quizzes. So you still got 3 more quiz and can help you to pull up the marks. Okay, these questions are quite long. Is there any question you want specifically you want to see or discuss about the solution? Let me see. Interesting. So one thing you look when you see the proof question, right? When I put out the proof question, don't try to think that try to think from the definition. Okay. So whenever I put out the proof question, you should try to recall all the definition in the question. So similarly to this tutorial question, so when you see some proof question, you should try bring up all the definition, okay, and then see what you want to prove, okay. The proof question I gave usually is like just spell out the definition, you will get the answer. You won't need to do extra work, okay. You just spell out the definition and then know what you want to find, and then do a simple twist, or even it will fall out from the definition. You don't need to do a special trick. But in the exam, of course, I put some hard questions, or maybe you will get stuck. But usually I won't put some hard questions. Any question you want to see specifically? We don't have time for every question. Okay, maybe we try discuss 4A. So 4A says that A and B is in the relation if only if A is taller than B. Okay, is it reflexive? So is every A is in the relation? No, right? Because you can't be taller than yourself. How about symmetric? If A taller than B, is B taller than A? It's impossible, right? So no. Anti-symmetric. So if A is taller than B, B is taller than A, then A is equal to B. Okay, but the reason is wrong, I think. If A taller than B. Okay, yeah. So the statement is if A is taller than A. If A is taller than B and B taller than. I think the reason is wrong, right? It is not symmetric. Let me think. If A is taller than B, B is taller than A. Okay, I think this is true because the proposition logic. Okay, let me write down the. Yeah, so how I work out this is write down the definitions if so I think this is wrong, right? Is that right? You reckon? You reckon that's wrong? False implies true. Huh? So this is true. Yeah, I think this is true. False implies true because this is false, right? This part is false. Right? Because you cannot get the condition if A is taller than B and then B is taller than together. If this one true, this one false, and is so this one's false. So this one actually yes. Okay, I need to change the solution. So this one is yes. To change this. So maybe I put it that first, and then I square it. Okay. Transitive if A is taller than B and B is taller than C, so A is taller than C. Okay, this one. Maybe try one more. Okay. So if A and B is in a relation, it can only if A and B were born on the same day. Yes. So you and yourself were born on the same day. Yes. And you cannot split yourself into two. Right? Symmetric. If A and B were born on the same day, then of course the B and A were born in the same day. It's the same thing, same person. Antisymmetric. So if is it antisymmetric? Okay, it is not right because you can have two different person that born in the same day. If A, B born on the same day, B, A born on the same day, it can be different people. It can be different people. Okay. No need to be the same. Sensitive. So if A, B born in the same day, B, C born in the same day, so I think it's quite automatic A, C born in the same day. Okay. About this kind of question. Okay, so xy is in the relation if only if x plus y is equal to 0. Is it recursive or not? No, because s plus s is equal to 2x. This is only true when s equals to 0. So you can just pick 2 plus 2. So 2 plus 2 is 4, not equal to 0. Okay, symmetric. So if s plus y equals 0, is it y plus s equals 0? Yes, because addition is commutative. You can solve. Antisymmetric. If x plus y equals 0 and y plus x equals 0, is it true that y equal to x? No, right? Because you can pick y and minus 1. Okay, so minus 1, 1 plus 1 minus 1 is 0. And then if you sort the order, it's also 0. Okay, if you don't know what I'm showing, you should have a list of definition with you. Okay, put a definition on the right side and then check the argument here. Transitive, if x plus y equals 0 and y plus z equals 0, does it imply that x plus z equals 0? Okay, so the claim here is no. Okay, why no? Because you can consider 2 minus 2 and minus 2, 2. So 2 minus 2 is 0, minus 2 plus 2 is 0, but 2 plus 2 is 4, which is not 0. Okay, so it's not transitive. Okay. Go to another one. Maybe try this one. So Sy is in a relation if and only if xy greater than or equal to 0. So reflexive, yes, as x plus x is x squared is greater than or equal to 0. This is the first lecture we see. Okay, square of the number is always greater than or equal to 0. Symmetric or not? Yes, because if xy greater than 0, you just swap xy equal to by x. So multiplication is commutative. Anti-symmetric? No, because if you know that 2 plus 4 is greater than 0 and 4 times 2 is greater than 0, it doesn't mean that 2 equals to 4. Okay. Transitive. So 1 times 0 is greater than or equal to 0, and then 2 times minus 1 is greater than or equal to 0. Is it true that 1 times minus 1 is greater than or equal to 0? No, because minus 1 is less than 0. Okay. Yeah. Minus 1. Okay. Okay, so this kind of question is already like a calculation in the equivalence relation topic. So you should know how to check these properties. This one, proof question for fun. You can go and try. This one also. This one not quite. This one also checking the equivalence relation. Yeah, this one. Yeah, this one also checking equivalence relation. What is this? This one is actually a fraction. You are defining a fraction here, a over b in the disguise. This is actually a over b. Okay. This is actually a rational number. The set here. So rational number is actually a equivalence relation. So these are actually how to put it. Just say that this is a rational number that is greater than 1. This set here is actually rational number greater than 1. So rational number is actually a equivalence relation, right? Because if you remember, 1/2 is equal to 2/4 is equal to 3/6 equal to 10/20. So actually, rational number is an equivalence relation. This is one way to build out the rational number. Okay. Like this. So rational number, equivalent column. This one. Okay, I will put up the solution and then you can check. And then if you think that my solution is wrong, you can email me or next week. Next week? Oh, you are not affected, right? So next week, so this week, have a break from Thursday because of the general election. And for those who go back for voting, anyone go back for voting here? Hold on. Go back for voting, Malaysian? No. No one's go back for voting. Anyone go back for voting? Who? Can I see a hand who will go back? Huh? Who? Only 2, 3, 4, 5, 6. No one's else. Okay. Please vote for a better Malaysia. Okay, see you after the general election with a new prime minister.
index set 它有
有没有什么property？通常我们会让它活在 natural number 里面，所以我们可以 list 1、2、3、4、5、6、7、8。通常
就 I 一般属于 nature